Okay, I've taken the basic Ainsley MOSFET circuit, which switches an inductive load through a MOSFET and claims to be producing excess heat, which claim, of course, is wrong. But what I've done is I've used good technology and good construction to make a MOSFET switcher. This is an H-bridge or X-bridge MOSFET switcher. And that's the power section. That's the MOSFET temperature. And I am switching that MOSFET with this pulse width modulated circuit here. Let's see. So we have a pulse width modulated motor controller chip with a duty cycle and frequency control. And that is switching this little X bridge under the fan there. Let's see, where is it? There it is. There's a 4-transistor X bridge or H bridge there, which is acting as a gate drive circuit for the MOSFETs. That goes through here and through these two little trifilar toroid transformers. And those wires there, 1, 2, 3, 4, 5, 6, 7, 8. And that's providing the gate drive pulse for the MOSFETs. 1, 2, 3, 4. Those are IRF 640s in there right now. And the input power that's being switched is coming from this power supply over here. There's a transformer and a bridge and a couple of filter caps. And that goes around through this wire and through this wire. These switches control the current flow through that wire, and then that goes in to the primary MOSFET switcher, which then has an output, and I'm using that output to switch an inductive load, which is 11 turns of number 12 automotive primary wire, and 540 turns in an air core resonator, and a top capacitance made out of a couple of Chinese stainless steel bowls and some aluminum ducting, and a breakout point up at the top right there is the breakout point. Okay, so let's see what you can do with a properly switched MOSFET circuit. So let's see, this is by the way the tinsel coil, SSTC, a tinsel coil, SSTC. And here we go. Mains power on. That gives us a light on the DC power supply. And this switches from half bridge, standby, full bridge mode. And this turns the oscillator section on. This LED indicates that the oscillator section is on. This LED will indicate that this is an RF, this section here is just a little RF pickup that will turn that light on when the system is in resonance through RF pickup. And if that light comes on, that indicates that the MOSFETs are overheating. And this is the MOSFET temperature of this MOSFET right here. Okay, so now we're going to switch to CW mode, like that. And what's going on up here? Aha! So there's a power arc right there. I'll move that aside. Ow! Whoa! I almost blew my camera. Got a shock from my camera, actually. But anyway, there's the nice power arc. That is an electric flame right there. You can see that electric flame. Let me give here's, if you wonder why the end of my pointer is black like that, it's because I do this with it. You can see how hot that electric flame is. A beautiful Corona display there. Hot Corona. My bamboo chopstick instantly bursts into flames from that. And yet, here I have to put the camera down for this because I don't want to take a chance of blowing it. Okay, so maybe you can see that. So now, remember how hot that flame was? So here I've just got a screwdriver in my hand, and I'm drawing that arc right to the screwdriver, and I don't feel anything. This coil is running at 1 megahertz. See there? That's just right in my hand. And I can pull a nice electric fire off of that. Like that. So this is what you can do with properly switching MOSFETs. So there is the tinsel coil, a tinsel coil, and a properly constructed MOSFET bridge, and switching an inductive load coupled to an air core resonator, and it's producing a hot power arc. Less than 75 watts input, and you've seen how hot that arc is. Tinsel coil, SSTC.